super close to the surface, it's going to be moving very slow. So you're not getting great heat transfer because your velocity is lower. Welcome back, guys. Welcome to another video, and today we're going to be looking at the aerodynamics of a U-Haul. And I have seen this. You can see this here in the let me get the full cam. There we go. The wisps here. Have wondered, like, I saw that when I was traveling on the interstate or whatever. Like, is this just marketing BS, or is there actually something to this? So I'm curious to see what this video details and see what we learned from it. So if you're new here, I'm a mechanical engineer, a private pilot, and I'm a 3D printing guy. Just like to look at videos and try to learn and maybe explain things further and give my point of view on things as a mechanical engineer. So if you guys could leave a like and a sub maybe, and look forward to diving into the video. There we go.
While walking around my neighborhood in Austin, I saw this advertisement on the back of a U-Haul.
Now, I don't know about you, but when I think of U-Haul, I don't think of aerodynamics. So
I always wondered what this guy kind of looked like. His voice is very good for a narrator, so it's kind of cool to see him in real life.
I'm gonna put their claims to the test. I'm gonna make U-Haul go hypersonic, but not this U-Haul.
I'm going to make this U-Haul go hypersonic.
Yeah, depending on how things are going, we've got a mechanism. We might even be able to just cut this loose in an empty test section and really see how dynamically stable this guy is at Mach 7.
Mach 7. Interesting. I like this. I think what they're going to get into is CFD and fluid dynamics. I think that's really cool. Got to do some of that simulation wise in class. I can actually pull some of that up quick.
A few moments later.
Okay, so here is actually a just short snippet from ANSYS, which is a pretty well-renowned simulation software. So basically, my project was a wing and ground effect, and if you didn't know, airplane wing when it's closer to the ground within, I believe, basically the wingtip to wingtip length above the ground, it's in ground effect. And basically the wingtip vortices can't spill off the end of the ends of the wings and create drag. And so you get this extra cushion of air, and it reduces drag as well when you're closer to the ground. And you can feel it when I'm flying. You just kind of float there. You can really drop down in your speed, 5 or more knots lower than what your stall speed would be, and you won't just drop out of the air. So here's kind of just a little snippet, and you can see the stuff on the end swirl around. Play it again there. So I find this stuff pretty interesting. So we'll see where this gets going into, and they'll probably, if I'm guessing, if I'm a betting man, they're going to get into dimensional analysis, because unless they can really yeet that wind going like Mach 7, we'll see. But dimensional analysis, we can talk about it if they get into that.
This is the stupidest video I've ever made.
That's quite the thumbnail. They should have used that for the thumbnail, man, on the wing of a bomber. That's pretty sick.
So, I'm on my way to the University of Texas, San Antonio, about 2 hours south of here. They have an extremely rare piece of equipment, a hypersonic wind tunnel, managed by none other than Dr. Chris Combs, who you may know as the laser-eyed hypersonic professor on Twitter. Dr. Combs is currently using it to test control mechanisms.
Let me know if you've heard of this guy before. I have not.
For hypersonic vehicles traveling in the upper atmosphere. I'll let the man himself explain the difficulties in controlling a hypersonic vehicle in the upper atmosphere.
When you go up high altitude, all right, you get high enough up in the altitude where control surfaces like flaps and fins don't work anymore. There's not enough drag, there's not enough aero force for that to happen. But you still need to be able to move around. And so usually we use control jets. And so like the space shuttle, a lot of space vehicles, you see those using the little RCS that fire.
You see that in the Falcon 9. All right, so here in this video, you can see little spritzes. The Falcon 9's using those to control its attitude there in space. And then once it gains enough velocity there, you just saw it, there it again. It uses the grid fins for drag, and it can directionally control the top of the rocket. So so pretty cool. Oop.
And when you're out in space, like properly in orbit, you're not worried about interaction of aerodynamics that's happening with that. But there's some middle ground where you're high enough up in altitude where the flaps still aren't effective, but you're low enough where you have aero forces happening. And then suddenly you have this hypersonic airflow hitting your jet, and it rips the jet apart, and you lose effectiveness. And NASA has even seen that for certain tests, you imagine from a
Mom called, or rewind here for 5 seconds.
that for certain tests, you imagine from a Newton's laws perspective, you fire a jet one way, you move the other way kind of thing. That interaction gets so complex that sometimes you fire the jet and you move the same direction.
Interesting.
That's a major problem for the new wave of hypersonic aircraft being developed. You may be surprised to learn that ICBMs travel
Falcon 9.
much faster than any hypersonic vehicles being developed. Intercontinental ballistic missiles are designed to exit Earth's atmosphere, travel extremely quickly at speeds of up to 7.8 kilometers per second through space, and then
7.8.
Air,
Today, Junior?
Whatever. I'll flash it on the screen, whatever it is. Fast.
through space, and then suddenly dive on their targets. They move quickly, but their lofted trajectory gives them
Isn't it kind of sketchy, though, that there are like 20 of those in an Ohio class sub that's just whizzing around the ocean that we don't know where it is, and they do? Well, the American government, at least. And same for Russia and probably China. It's kind of sketchy out there.
their enemies more time to detect and aim anti-missile defenses. Hypersonic missiles are designed to cruise within the Earth's atmosphere at about half the speed of an ICBM. The atmosphere slows them down, but their low trajectory means they suddenly appear on the horizon, previously being hidden by the Earth's curve, giving their targets minimal time to detect and intercept them. So this hypersonic wind tunnel is an extremely useful tool for companies and government agencies looking to develop hypersonic vehicles. An extremely useful tool that we are going to use to test a vehicle designed to move your old furniture across the country at Mach 7.
I'm curious what they use to power this wind tunnel with. Like, is it a jet engine? Is it a EDF or something to that effect?
So it will go, they'll face this way because airflow is this direction. I'm assuming you don't want this going Mach 7 in reverse, right?
Would it reverse, Terry?
So it'll get mounted facing like that, somewhere in the middle, right? Yeah, hey, maybe that's a stretch goal, depending on how much time we have.
We do have multiple of them.
Yeah, so it's gonna sit right here like that. Should we go ahead and unbox this guy?
Yeah.
Is it? Yeah.
Someone's gonna get it.
Yeah, we're gonna upset a collector somewhere. I'm sorry, whoever's out there watching this. That's a U-Haul model collector.
It has the original price on it of $7. I got it for $40.
Yeah, I mean with inflation,
$40.
who knows how much that's worth. Okay, so yeah, it's gonna sit. We're gonna take the flat plate out. It's gonna be mounted like that on the Sting. Eli, you got a demo for us for what kind of Sting mount we're probably talking about?
It'd be cool to be a college kid at, a university like this. My university didn't really have anything like even remotely close to this, but this would be really awesome to be able to work and play with. The closest thing that I probably worked on was when I was a lab tech in the lab, fabrication lab, and there's a senior project with a jet engine, and that was pretty fun to play with. But that's the closest I've got to being hands-on with like a little jet engine wind tunnel thingy like this.
Our variable angle of attack strut that still has a cow on it from a couple weeks ago.
Yeah.
Oh man, that poor cow. Jeez. This is you guys have probably seen the meme of the aerodynamic cow. Dynamic cow meme. Yeah, here we go. That's probably where this stems from. Looks like they did an elephant. I don't know. There's just memes of a cow being, I guess, aerodynamic. I don't really know.
But yeah, we'll need to mount, because this has a 1/4-20 thread in the back, so we'll need to figure out how to mount the U-Haul.
Yeah, so we'll gingerly remove that cow, I think.
Poor thing.
Yeah, exactly.
That's nothing that the vets don't do to you.
I like this guy's shirt. PhD, an academic that solves problems you didn't know you had in ways you don't understand. See, also brilliant wizard. I need a shirt like that.
That's nothing that the vets don't do to you. That's when I decided not to be a vet.
That
when
left
I went
a mark.
on a house call, and they're like, "This is what your job is now."
Yeah.
The results for that cow are excellent. Groundbreaking bovine technology. So
that was using the Schlieren imaging. It basically uses a series of mirrors and stuff. I've seen that in other slow motion video. So you can see the shock waves, and it's really cool. So that's a bullet traveling. You can see the shock waves. So really puts into perspective that air, really the atmosphere we have around us is more of a fluid than anything. It's really cool to see that. You can see the turbulent flow behind the front of it there. Pretty crazy. He does a lot of cool stuff.
technology. So how does this wind tunnel get air to travel at Mach 7?
That's what I'm interested in. Compressor. I wonder if they do just a really fast release of air. I feel like that'd be very turbulent though.
On one end is a big old vacuum
See?
chamber, and on the other is a pressurized tube. The two sides are separated by a metal diaphragm that is designed to pop at a target pressure differential. You would think that increasing the pressure would increase the speed of air traveling between the sections, but it doesn't.
One other little nuance is people think that you can, if you increase the pressure, that should increase the Mach number, right? That kind of conceptually makes sense. Our Mach number is actually fixed by the geometry. It's just all about expansion ratio. So changing pressure just changes the Reynolds number and the mass flux and the equivalent altitude that you have, but the Mach number is 7.2, basically regardless of what diaphragm that we use. And that's fixed by this shape.
That shape is the shape of the nozzle, which works exactly like a rocket nozzle. Rocket nozzles work by speeding up exhaust gases from subsonic speeds to supersonic speeds in the converging section.
So, a couple things. This is Bernoulli's principle to a T right here. This is why planes fly. So you have a so low velocity, higher pressure airflow over here in the larger diameter. Then it necks down. You have a higher velocity, lower pressure section. So that's why over the top of the wing, let's see. Yeah, so you got your airplane wing cross section. Bloop. And yeah, here we go. So you have a virtually flat bottom. So your air is only having to travel, it's just traveling at 200 miles an hour, let's say. And the top, it has this extra distance because it's not a straight line. So think of the hypotenuse on a triangle. It's a longer distance. And I guess maybe that's not the best analogy, but it's a longer distance. So the air has to travel a longer distance, making it have to move faster. Think of it like, let's see, a track, runner's track. So if you're going around the outside of the track, you're running a longer distance, if that makes sense. So you're running a longer distance around the outside of the track versus the guy who's running on the inside. So to keep up with the guy on the inside, this guy on the outside would have to run a lot faster. So that's what's happening basically to the airplane wing. This guy is having to run a lot faster to get to the same part as this other guy on the bottom part of the wing to rejoin in equally. So you have a lower pressure, which goes back to this image. You have a lower pressure at a higher velocity. And then the Reynolds number that he talked about, so that has to do with whether flow is turbulent or laminar, which you've probably heard maybe those terms before. whole bunch of calculations. We did this all the time in fluid dynamics. So goes a lot into this Reynolds number is important for a lot of different things, for drag, for heat transfer. If you have laminar flow in heat exchangers, for example, the AIO, the cooling block in my PC, all those little fins and everything's that it run, every surface, any of the surface area that the fluid or air or whatever runs around, it's going to have a boundary layer. Let's see, boundary layer. And you want a turbulent. Okay, yeah, perfect right here. Laminar, turbulent. So with laminar, you have this gradient here. So any of the air moving at the, super close to the surface is going to be moving very slow. So you're not getting great heat transfer because your velocity is lower. So you're not transferring as much fluid, whatever, over it and cooling it as quickly. So that's where you get, it's warmer. It's, and then so once you get turbulent flow, that's a lot better because it breaks up that boundary layer and you get a lot better heat transfer. So it's important for a lot of different things, but that's one of the applications for Reynolds number.
Hitting Mach 1 at the throat.
But you also can determine your flow based on velocity and all the other things that feed in to determine your Reynolds number to find out if it is laminar or turbulent. So yeah, I forget how you pronounce that one, but density, speed of flow, dynamic viscosity, and then kinematic viscosity, and then it gets into all those things. So I haven't done this for a couple of years, so I'm a little rusty, but I have all the stuff from it, and I've done it before.
At which point, the physics do a 180 turn in rules.
And so what happens is, it's just like traffic on the interstate. If you put I-35 down to one lane, everything stops, all right? Everything's going slow. You add lanes, 3, 4, 5, 6, everybody's able to speed up and spread out. Air molecules do the same thing once they're going faster than Mach 1.
My friend, not just bikes, might have some arguments for that.
Yeah, right. And so you could expand this out more and go higher Mach number, but then you get limited on the expansion end because the pressure's getting lower, the temperature's getting lower, and we're actually already pushing the limits of rarefication with this. So the reason that we have insulation there on that piece of pipe behind you is because we actually heat up the air. So these are big cables that power electric heaters that are wrapped around this pipe. And then we have insulation on it so you don't burn yourself, and it also keeps the heat in. All right, we can heat this pipe up to 700K, 800F.
What's the purpose of heating it?
But so that the air doesn't freeze in the free stream. Because even when we heat, the free stream air basically equivalent temperature, like if it was that, if you were in the upper
expansion.
It's the expansion. So the energy has to come from somewhere. You can't cheat, right? And so that energy is all going into the momentum and the velocity of the gas, but you lose the pressure, you lose the temperature. So it all gets sapped out from
What
that
effect
side.
would that have on the test? It wouldn't literally freeze, I assume.
Yeah, so what happens is, really you scale it out with Reynolds number, basically. And so it's on the one end, the pressure being low is more of an altitude consideration, but then you have temperatures that aren't realistic.
Right.
All right, and this is a problem in a lot of hypersonic facilities that we have too, because this is still a cold tunnel. We heat up to 700K, and that's still cold because the free stream equivalent air temperature that we get is 60K. All right, so minus
Kelvin, by the way, when he's saying K. So subtract 273, and then that's your Celsius measurement. So 60K, that'd be 110 Celsius negative, so pretty cold.
Hundreds of degrees. It's cryogenically cold. Really, and that's just above the liquefaction point, all right? So you're really just heating
so that... you're actually keeping it above the liquefaction temperature.
Exactly.
So
that's all you're trying to do.
Liquid.
Yeah, so it won't basically, you won't get condensation, you won't start to have things turn into liquid. And that's really all we're going for. Because to get a true flight enthalpy, we'd have to heat up to 2000K or so, which you hit material limits for stainless in your driver tube pipe, things like that. So there are very few facilities that actually operate that way. You have to go into a completely different mechanism to run those types of tunnels.
So, in summary, This machine essentially builds a pressure differential between the vacuum on one side and a long pressurized tank on the other to drive air through a converging diverging nozzle. This pressurized side is designed to be as long as possible because a longer tube equates to a longer test. The test may occur in the blink of an eye, but with a high-speed camera, we can capture a lot of data when a long column of air is traveling by instead of a short one. So, onto the test itself.
There's the Schlieren imaging setup there.
But it wasn't all smooth sailing. When we started to pressurize the system, some pressure gauge readings started to glitch out. And this was a big problem, because those pressure gauges were needed to trip the camera trigger box.
Without the triggering
Kind of
box,
important.
we have to manually get the camera to record when it's supposed to.
Right.
And we have basically a 1 second window of camera buffer. So Eli is either gonna fix the trigger box while in the 40 minutes that the vacuum is getting pulled down, or if he can't fix that short, then we're gonna sit here, and then when we hear the diaphragm burst, smack the trigger button, and that should catch it.
Should.
Okay.
So that's the status right now.
And so began a mad scramble by Eli to find the source of the problem.
It always happens when you're working on something for presenting it, or crap always goes wrong. Moore's law. He shows up.
We knew the problem
Murphy, not Moore. Murphy.
was being caused by a short circuit, so it was a matter of unplugging everything until we could track down the faulty part.
That's fun. It's always fun.
With only 40 minutes before the test was due to start, I was clearly anxious. But with all hands on deck and Eli's understanding of the machine, we did manage to find the culprit and proceeded to smash it.
There we go. We got some shrapnel.
For the last hour and a half.
Freaking microcontroller.
So it's just the Arduino board was broken?
Yeah, it was running the code, but it was not outputting the voltage.
Okay. So you just replaced
Yeah,
the
just
Arduino
pop
board?
in a new board. Worked fine.
With that, we could finally get the tunnel up to pressure. But first, we had to lock the place down for safety.
Now, the last thing I'm gonna do is to let the surrounding labs know that we're gonna pressurize. So we have a laser bell that will ring to let the other labs know.
A laser bell.
It may not be obvious there, but when I heard laser bell, I assumed it was some sort of overcomplicated sci-fi laser actuated bell and was clearly confused.
A laser bell.
Only to slowly realize that it was in fact just a normal bell to tell people a laser was in use.
Oh,
So like
it's
3 short.
to tell
and then a
people
long.
that there's
Yes.
a laser in.
This is important because when you have pressurized gas that can expand and something pops off and it blows up, obviously it can be very dangerous. A better way to do it, well, I mean, not in this scenario, but ways things have been made safer is they use water to pressurize it. And so water doesn't, contract, or it's not non-compressible. So when you pressurize water and you have a leak or something busts, it just spills out. So engineer I was talking with, I believe it was my professor, maybe even, they filled the airbags in car suspensions to pressure test them with water instead of air, and so they wouldn't have shrapnel literally flying everywhere. It'd just be water, and just bloop, it would just burst and everything. So keep that in mind if you're doing a test kind of like that, so you can make it safer that way.
Okay. These lasers will blind the shit out of you. Had enough? I'm not sure doing this on camera stuff was the right call. At this point, we just had to wait for the pressure differential to get high enough to burst the diaphragm.
Now we just hope it doesn't get to 300 and not burst. Then we're like, what's going on?
These diaphragms with this score depth can burst safely to 320 psi.
Yeah.
I don't know if I trust the model to survive a 320 psi burst.
Yeah.
Though.
Have we been?
So, okay.
That was not the sound I was expecting.
Yeah.
I was expecting like like a big release, like a cannon almost. I agree with him.
I was expecting a bit more of a boom than
Yeah.
like
Yeah.
a prolonged fart.
Yeah, it's like a big metallic fart.
Yeah. So I turned off the buffer tank so we're not still pushing air through there. If you want to turn off the right to file, just so we don't save excess data.
Wait.
So
Hang
that,
on. Will you do this bit? 'Cause I
Yeah.
don't want
Yeah.
Yeah.
Okay, absolutely. All right.
to. I want to lose
So
the
I'm going
data.
to stop the right to file. Then I'm going to turn off the vacuum pump. And then before we all go out there, I'm going to poke my head out, do a safety
Okay.
check.
So, the group of overexcited nerds headed outside to review the high-speed footage.
Okay, there goes the release. So it's flying now. Oh yeah, this is great. We've got the bow shock set up. This is perfect.
What?
Yes,
Did we get it stable?
we got it. The U-Haul's stable.
Oh my god.
Oh, it's starting to tip down now.
Oh, that's incredible.
Oh wow.
Oh my god.
You can really see that that flow over the top there. Looks like some eddies maybe there as well. It's really cool. See it coming off the front bumper, and then it's turbulent right here, and then it gets shoved off the top.
Almost stable in flight.
Yeah, it's starting. As the more it tips down, the more it's catching the hood.
Yeah, right.
Wow.
Unfortunately, the viewing window for the test is pretty small, but in the words of Dr. Combs, I don't know what we learned, but I'm excited. The two bow
It's cool. It's really cool.
shockwaves result in some funky shockwave interactions. On our static test, where we fixed the truck in place, the cab vibrated wildly, which honestly, the fact this little plastic model held up to a hypersonic blast of air is impressive.
Right, no kidding. Even a real truck up to that speed would be like in a million pieces.
So, with all this data, we do get an idea of how a hypersonic U-Haul may behave. So, I had our wonderful animator Eli create an artistic depiction of what a full-scale hypersonic U-Haul test may look like. Science. It's a wonderful thing. So what did we learn? That Dr. Chris Combs is a fun guy, that hypersonic wind tunnels are pretty neat, that I need to learn to speak more clearly on camera, and that U-Hauls are absolutely not designed for hypersonic flight. But the thing I'm most curious about, what became of the U-Haul model? We may need to wait a year or two to find that out.
And then,
Probably went into the back of that big vacuum tank.
like I said, hopefully, maybe we try a free flight test. That
What
could be a
will
lot of fun.
actually happen? So you just let it go and it just flies back? Is
Yeah.
there like a mesh back here or something that will catch it?
No, it's gonna go
Into the
flying into the vacuum tank.
You're not afraid?
There's a graveyard of models down in the bottom of that right now, and periodically we get an undergrad to go fish stuff out. It was funny so this vacuum tank was custom. There's this company in Ohio that makes vacuum tanks like this, and when I called them to one of the conversations we had where we were, kind of speccing this thing out, and I said, hey, could we put some extra access flanges on the side? And they're, oh yeah, sure, no problem. How big? And then I'm kind of just thinking out loud on the phone. I was like, about how big do you think it would need to be for a student to fit their
Yeah, it's
arm
like-
inside? And they're like, what are you making, man?
Yeah, I was like, who's our smallest grad student?
Yeah,
that can
right.
fit into this thing.
Yeah, I mean, I do joke that it's big enough to fit grad students in there that have misbehaved, as sort of a threat.
So, if we've learned anything, you don't want to misbehave in Dr. Combs' program. But you can still learn from him in the safety of your own home. I've uploaded our uncut tour of the hypersonic wind tunnel to Nebula. It's over 27 minutes long and full of fun moments that I would have loved to have included in this video.
Cool. Well, that was interesting. Definitely enjoyed talking about the Reynolds number and some stuff I've done with FEA and things of that nature. So you can, if I would do anything as far as like a master's or a PhD, which I'm considering, it would be in aeronautics or fluids, something of that nature, because I just really find that interesting. So maybe we didn't get the answer of whether it's more efficient or not on the U-Haul, but I guess it probably couldn't hurt. Would be curious to see what the coefficient of drag is for the model that they're claiming or whatnot. But yeah, pretty cool. If you guys liked the video, give it a like and consider subscribing. I would really appreciate that. That's all I ask in return. Help me grow the channel. And let me know what you thought about the video, this one, or the one we watched here. Give me your thoughts down below. And see you guys next time. Peace.